Testing, testing.
We need to share screen. Testing. Okay, well, let's take a time. I think we're good.
Okay. So everybody hears me very well. Hi. Okay, sorry about the technical difficulties. The first one I've decided to log one of computers out of its system for nobody knows which reason. So anyway, welcome back everybody. So this is the last couple of lectures about the series on amplitude analysis on the quest for Exotica. I know it's Friday early morning. You are wondering why did we start at 9 o'clock? I am wondering too. So we will go slow. So this series of lectures, I mean, these two are going to be a bit more dense, technical and specific than the previous two. So we are going to play and use things that we saw on Wednesday, and then from there we're going to do that all the way to very sophisticated amplitude analysis for meso-meso scattering and other reactions. Okay. So I don't know if you remember, but at the very end of the second lecture on Wednesday, we ended up with a slide like this. And the idea was, regardless of if you are working on experiments or if you are doing lattice QCD simulations, in spectroscopy, we are always going to need to describe this set of data. For example, for the phase shift. There is no way around it, and it's the only possible path towards understanding the spectrum. So we have to do what we call amplitude analysis. Now, thing is, we don't know the explicit answer. We don't know the explicit formula because this could be solving QCD. There are many ways, many effective field theories and models depending on the regime, but we are not going to go that way. Today, we're going to use what we call a bottom-up approach, which is we are going to impose these first principles. Don't you worry, I'll explain the three of them. We already know unitarity, we don't know the other two. And we're going to just use these first principles and the data information, just using data from experiment or data from lattice QCD in order to obtain our observables. Okay? So first things first, because we're going to play with this, we have a particle A decaying to B and C, and let's say that A is at rest. Then we can describe the system, the final state, with a given collection of quantum numbers. I don't care much about the details, and we are always going to use particles without spin, because remember our final states are going to be pions, kaons, etas, etc. But the idea is that we can describe this final state system. Let's say that we are describing everything on the direction of C, on the particle C. In polar coordinates, we will end up with something like this. So this is going to go many quantum numbers that we are not really caring about now. And then we will have part of the wave function that depends on the polar coordinates, right? Which means is this integrand, if you were to get the norm of it, would be called the intensity and could be basically the probability of getting events on this direction in polar coordinates. Okay? What I care for you, well, first things first is to realize that this can be related to the amplitudes we're going to be talking about today. Remember, for angular momentum, because I'm lazy, I will be using either capital J or this QL. And the intensity, to calculate the norm, will be proportional to these functions. What are these functions? How are they called? Probably you know them. Spherical harmonics, very well. So you can calculate them. There are recursive relations, and if you go to Wikipedia, you will find tons and tons of tables. These are some of the simplest ones. Again, this is because the particles in the final state have no spin. Otherwise, this will be D functions, which are rather more complicated, but we aren't going that way today. So you know some explicit expressions, and we know something about the intensity. And you will see we will play with that later on. So also remember that we are taking a look at the states, particles, and so they have well-defined angular momentum. We just have to claim, well, we just have to state that our theory is invariant, is rotationally invariant. And so the angular momentum arises as a good quantum number. So our amplitudes, whatever we measure at the end of the day, can be described in terms of what we call partial waves. And this is doing a partial wave projection. And these are where, well, the functions where our resonances or states are going to live. So let's start by describing how to fit data. So we know that unitarity tells us the conservation of probability. This S matrix must be equal to the identity. So let's start by elastic unitarity. We have just one system. A goes to A. Pi pi goes to pi pi, and there is nothing else. In that case, it is no longer a matrix, right? It's just a function. It's just one entry of the matrix. So the function, the modulus of the function must be equal 1. Basically, in the angular momentum projection, we would say that S of L is equal 1, the modulus. This means that we can describe it as just phase. I'm using this, 2I times delta for convention. You could describe it as I times 5, and that would be your phase over there, right? What does it mean for T, for our actual amplitude? So remember the relation between the two of them. This means that for T, and I should have called this little one T hat, the relation is something else. And I leave as an exercise to prove this relation. It's not very complicated. We can talk about that afterwards. So we know the way of describing these T functions. We have to invent something for this delta, and then we will be able to describe our data.
Can you remind us briefly the difference between T and T hat one more time?
Yeah, sorry. So I should have used T hat here. So it is just a convention of the way you define it. The difference between this T that I'm defining here and what I call T hat is just the phase space. So you can add it or subtract it. If you add it here, then the relation for the partial projections here, we have a phase space of 2 times Q divided by the square root of S. If you define T hat, then the relation is 1 plus 2I times T, little t. So that is the only difference. It's just a convention. So you can use both. We use both. This one is basically, as you can see, it's kind of like normalized to 1. This one will always have the phase space inside. At the end of the day, it doesn't matter. You are going to measure some amount, and then the phase space is always there. You can add it, well, leave it there or subtract it. So let's start by doing the simplest thing that we can for this delta function. So let's assume that we are at the threshold of the reaction. So you have 2 pions that are interacting right at the threshold where the masses, where the energy is basically the sum of the masses squared. In that case, this delta, threshold is going to be 0, right? There's no scattering. They cannot interact because you don't have enough energy for them to interact physically. But if you are slightly above it, then you might have something that is not 0. Okay, we are going to describe it in terms of Q. There's a first order expansion approximation. Actually, it means that for T, this will be proportional to this parameter A. Can somebody tell me what is the name of this A? The scattering length, right? This is very important for us and for many, calculation theory practitioners, knowing scattering, and also if you work to study nuclei, you might want to know about this in volume reactions. If you go along this line and you use this approximation, then the total cross section, remember, and we will prove this today, the imaginary part of the little t is proportional to the cross section. So basically 4 times pi a squared. Okay, assuming that there is only one angular momentum that contributes to the cross section. So what happens when we fit data? Okay, let's say that you want to do something more sophisticated. So instead of using just one order for t, you're going to expand this polynomial, many parameters, 10 parameters. Fine. Do you think that you're going to be able to describe this? Well, how many do you need? Let's take a look at that. First things first. Why q to the 2n and not q to the n? Okay, you can think about that. The second thing is, if you remember, this phase is associated to a pole in the complex state. Can a polynomial in the numerator produce a pole? It cannot, right? So it doesn't matter how many parameters you're going to have here, you won't be able to describe the full energy value. You would need something like this. It's a very simple formula, but this is not describing everything as we saw on Wednesday. So we still need something more clever. We have some expansion for low energy, we have some expansion for the simpler states, but we need something more general, right? Also, is this parameterization unitary? What do you think? This is a unitarity relation. This is preservation of probability. Is this parameterization unitary? I mean, let's do it. At first order, this is A times Q, right? But this is the imaginary part of A times Q if A is real. It's 0. But what is this part? It's A squared Q squared. So no, it's not unitary. We are breaking preservation of probability. That's not good. So let's do something that doesn't break the preservation of probability. Something that allows us to respect unitarity. Then we will expand and put, some explicit formulas over there. You can write, and well, you can play with this, or you can do it as an exercise related to the previous one that I asked you to do. You can write T in this way. Well, this is going to be a function, cotangent of delta, and then this is the phase space rho. This back here, but this is kind of breaking it. This is the square root of S divided into times Q. This is the phase space of the reaction. Now, this formula is unitary by construction. As it means that I can get an explicit value for rho or Q times cotangent. And whatever I put in there that makes sense with respect to unitarity. Okay? If I put 1 over Q, 1 over A, I recover the expansion that we had before. Okay, as an approximation. For example, let's relate this to lattice QCD. What would happen if we have some expansion like this inside a box? How do we know what we are looking for? So if you had a box like this, and then say that you have 2 pions inside the box. These 2 pions, as we were in a box, are quantized. So we produce some energy levels depending on the mass of the state, the excitation, and the momentums of these 2 pions, right? So basically, the ground state, they don't move. Quantization of one of the pions moving with 1 unit of momentum, 2 units of momentum, etc., right? Now, what would happen if you had repulsion in the system? In this customary, but not so customary definition of the scattering length, if they are negative, then we will have repulsion, which means that the energies that we see on the lattice, on the box, at the end of the day, are higher than the non-interactive ones, right? Why? Because they are repulsing each other, so the energy increased. If we had attraction, then the energies would be lower, right? So this is more or less when you see when you're playing with lattice QCD and you have your levels on a box. The first thing you should do is compare to non-interactive levels and see if you have an attractive or repulsive system. And, depending on the strength of the system, these lines will be displaced more or less from the non-interactive levels. Yep.
I'm sorry, can you also remind me what Q of S is?
Q of S is the momentum of the particles in the center of that momentum thread.
Is that the norm of the momentum?
No, this Q is the momentum.
Okay.
So basically, for example, for a system with equal masses, let's say that you have 2 particles with equal masses, Q would be something like the square root of S minus 4 times M squared. And then,
But it's a scalar quantity, not a vector
Oh.
quantity. It's a scalar, not a 4
oh,
vector.
this is a function. It's not a vector, it's a function. So, oh, yeah. Okay, I got it. Yes, sorry. Is the modulus of the yeah. So, yes. So once you have this formula and you know it's unitary, and you can expand it in whatever series you want, you get something like this. This is not the same as expanding T, right? Expanding T would break unitarity, but expanding cotangent would not. It will always respect unitarity, the way we define it. So you can describe the low energy region, but you could also, in principle, describe this energy region, the resonant one. So how does this pole arise in our system? It is simple, right? This is the formula. We have a denominator. So if you want to have a pole, well, this part must equal this whole part, right? It means whenever this expansion has 1 unit of imaginary part, then this will have a pole. This won't happen in the real axis. If these are real in the physical region, this cannot happen. But this can happen very close in the complex plane, which is where the resonance exists, right? Is what we were doing the other day. The resonance doesn't live on the real axis, lives slightly on the complex state. So we found ourselves a very simple way of describing lattice-fusion data or messy data from X-ray. And yes, we can describe something like this with a parameterization this simple, quote unquote. It's very simple yet powerful. Problem is, we were talking about elastic scattering, so everything were functions. How do we describe systems with lots of finite states? So let's see, we have A and B, pi, and then we are at an energy where we can have many different products, not only pi, but also k bar, eta, 4 pios, right? This is just a function. So you can only describe the elastic case. So let's move into that. This is called, what we are going to do is called the K-matrix approach. It's very simple, customary, we all use it nowadays, and it's powerful, as you'll see. So the first thing is, we're going to assume a first order approximation. Let's say that we are close to a resonance, okay? This resonance can decay to many possible channels. This is going to dominate the partial wave close to the resonance. And this is going to be a matrix, because now we have inelastic scattering. So the amplitude, the little t of L, is going to be equal to K, where K is a propagator of the resonance at first order approximation. We are assuming that this resonance has a very small width, and so we can describe almost as a propagator, and this indicates to many possible channels in fact. Now, because K dominates T, we can have more orders where K really scatters with itself. So the first order would be just K. But the second time, K would decay to all the possible intermediate channels, and then these possible intermediate channels would produce a K again, so the propagator again, that could decay, and then could scatter again, produce the propagator, scatter again, produce the propagator, so on and so forth. So you can keep expanding the series. And what kind of series is this? It's a geometrical, right? If you get this formula, you can back all the terms, then you recover this function. You don't really need to do that. You can always define t in this way. There's no problem on that. It's just mathematical construction. This is just a hand-wavy way of motivating it. But the idea is this: if you have resonances that decay to many channels, and if you have many resonances, I was asked on Wednesday, what happens when many resonances decay to the very same channel? Well, this is going to work very well. So we will see. But again, it's a mathematical construction. You can define it from the very beginning without doing any of this. I could have just introduced it and introduced you to the mathematical properties of K. Okay? You can also rewrite it this way. And this is basically, remember, this is the inverse. So the numerator is equal to 1. So the numerator of T can be made equal to 1, and everything can be put in the denominator as the inverse of this object. And we will play with that in a second. So now, what are the properties of K? There is a mathematical construction. I can define the partial wave in terms of this K matrix, and then I can define some basic properties. Well, the first one is time reversal. So our theory, we are going to assume that A going to B and B going to A are the same, and so it means that, so the order doesn't matter, and it means that K is going to be equal to the transpose. Okay, so K is equal to K capital T. One. The second one is unitarity. Remember that it means this in matrix form now, because we are no longer in the elastic region. And this, if we look at the formula for T, you can rewrite it as in this way. I leave it also as an exercise. There's no complete. Yeah.
Is there, when you're gathering things into the geometric series, is there an obvious reason why rho of S times K is like bound between 0 and 1?
Rho of S times K.
I never understand the argument when you do the like resummation and then they say, geometric series, but I know that the argument has to be between 0 and 1.
Oh, okay, understood. So you're asking me, why do we know it converges?
Yes.
Well, as I say, it's a wavy way of proving this. You don't really need to do any geometric series that works. Because you can just define it that way. And this respects unitarity as an algebraic construction. So you know what I mean. You don't really need to think about a series that converge. But you know, K as a propagator will always have a given coupling that is 1. Because it's a propagator, this thing is a bare propagator. This thing has a coupling that is ordered 1. Okay. Well, not order one, but some G square function. And the idea is that you are going to assume that you are in a region where those couplings times the phase space are very small. And so in that way, this wavy expression can converge.
Okay, thank you.
So basically, if I'm not mistaken yet, so the idea is if you put here a Baire propagator, and we will see the explicit formula in a few slides, then in the numerator of this propagator, you will have G squared divided by S minus M squared. Okay, that is the formula for the propagator. This G squared cannot be related to the width of this object. Okay? We will see in a second. So this G squared can be related to what we call gamma on Wednesday. If you all remember, gamma was this, what I call now, the width is the inverse of the lifetime. Okay? So now this gamma must be very small for this approximation to work. Because if this gamma was big, then this thing could be described as a propagator. So if I am doing it's kind of a circular argument, right? If I am doing this approximation, it's because I am assuming that the G squared that is related to gamma cannot be very big. And so the whole thing has to converge. Otherwise, then I cannot establish this argument. But as I said, this is just a handwave. You could have started with a mathematical definition like this, and then just keep going. Okay. So now we have time reversal, which means this relation, and the second one is unitary, which means that S times S dagger is equal to the identity. Also, it means if you play with that, if you calculate S times S dagger here, you are going to end up with the rest of KL minus K dagger L. And this is only unitary if KL and K dagger L are equal. Otherwise, you broke unitary. What does it mean for K? So we have that the entry AB is equal to BA, and that the entry AB is equal to BA complex conjugate. So the entry AB is equal to what? To the entry AB complex conjugate, right? We combine the two. This just means that K is real. And that is a basic property of the K matrix. At the end of the day, we can describe T with a K matrix, and if the K matrix is real, everything makes sense. Okay? And now we can accommodate or parameterize this K matrix. For example, in the elastic region, this formula that I presented you before is just the K matrix approximation, well, the K matrix approach, sorry. Just the inverse of the K matrix is equal to this. Okay? The way we define everything is the way. So let's take a look at this toolkit now. So we can describe either in the elastic or inelastic region everything in terms of this K matrix approach. Sorry. So this is K inverse. So there should be an inverse there. I don't know if I'm typing it or I didn't put this right. But the idea is, if I expand this in terms of a polynomial or the inverse in terms of a polynomial, we can recover some elastic things. This is now a function, the matrix, so it's no longer coupled setup. So I can describe elastic region, low energy or high energy, doesn't matter, describes unitarity, it's fine. If the data is very complicated and we have many final states, for example, here I presented you a pi measurement from an experiment, we're going to play with that. But this is not the only state that is open. In this energy, from 1 GB to 2.4 GB, there are many other possible decay. For example, where does the threshold of 2 kaons open? Remember the mass of the kaon? Is 0.492. 0.4926, yeah, depending on the kaon, more or less. So almost 0.5. So at 1 GB, 2 kaons open, right? So 2 pions here can decay also to 2 kaons. So this is just one of the many final states that we can measure and experiment. And we want to describe all of them. Okay? So here we are going to use a K matrix. We are going to use an actual matrix, not a function, to describe this data and the other channels. Now, this also answers the question that I had basically discussed about on Wednesday of what happens when many resonances decay to the same final state. They become something that overlaps. Are they simple enough? You see 3 peaks, and these 3 peaks are not going, they are not very far away. So they are overlapping. Actually, you see 4 peaks. There is a resonance in that tiny little ball. And then, well, we are indeed describing the data, indeed this fits in itself. So you can get all these resonances properly with this kind of approach. So you define a matrix where the number of elements, the number of rows and columns will be the number of final states that you are going to have. And inside that, you parameterize. And as I promised, this is the formula that you use typically for the propagator part, so for the resonance part. Two couplings, the mass, the bare mass of the system squared minus S, and there's a term that is usually smooth. And this can be parameterized many ways, like a polynomial with different variables, something very simple, very complicated. But the resonance part, usually the poles come from this one. Okay, so let's take a look at my fields. So let's go to the elastic field. So this is another reaction, pi scattering, and there you have lots of data and a field that goes to the data. Actually, you have two. They split here depending on the solution, but let's forget about everything that is above this dash line. We're going to focus on the elastic field. So we are going to revert back to a factor, no longer a matrix, but just a simple factor, okay? And it's going to be this parameterization. So if I go and feed the data, I'm going to feed it myself. So I parameterize this to tangent, and then I end up with fields. Now, this is just the real axis. This is where experiments live, right? You don't measure things in the complex plane, you don't measure things on imaginary energy. And this is this red line. This is actually the modulus of this function that I fitted there. This actually corresponds to that. So this is the phase shift, this is the modulus. Yep.
How are you looking at that plot knowing that the red box is the elastic region? How do you know that that's the elastic region?
Oh, yeah.
Looking at the plot?
Yes. So this is pi again, as I said, right? So it starts at 0.28 GeV, 140 MeV more or less. And so what else can appear here in the strong pole? There is a channel that can open in that region, that box, apart from pi. It's 4 piles, which opens at like 640 MeV. But 4 piles are so tiny, this energy region, that perhaps you allow me to neglect them completely. Okay. For sure, that is zero. And we have never determined that experimentally to be different from zero. So first order, there's only one side open, pi. So it can only indicate pi. If you were above this box, what is this? This is 1 GeV. So once again, one channel opens over there. 2 chaos. So then of this box, you do have open channels. There's 2 chaos and 2 piles coupled very strongly. That's also why you see this super rapid phase motion right over there. Okay.
What is the initial state of the decay again?
This one is pi. So pi interact with each other. They can produce something, and then they decay to pi. So we will see that there is something here, even though this say, right, this line say doesn't look at all like the right inner one that we described before, but there is still a state of it.
And what's the 0.6 to 1 GeV?
The 0.6 to 1 GeV.
Yeah, the data from 0.6 to 1 GeV.
This one.
Yeah.
So that is usually, well, that is a part of the collection of the CERN-Munich collaboration. So CERN-Munich experiments that were done in the 70s, 80s, at CERN.
I mean, what channel?
Oh, this is pi. This is pi to pi.
So I thought up to 0.4 was pi.
No, so this is what you measure in the final state. In this, the whole plot, the final state of the whole plot is pi. So you go on experiment, you have your interaction, and at the end of the day, you get some hits, right? And you can select the final state that you're measuring. This one is always pi. Now, the way of describing it depends on if there are other channels coupling to pi. Because if there are, I should put more than just one plot here. The plot to pi, and then the plot to KK, and then the plot to many other channels that couple together, right? And you have to describe all of them together. And this is the K-matrix approach. You have to describe all of them together to fulfill unitarity. Okay? But because I am neglecting all the rest, well, not that I am neglecting, all the rest are closed, what I can hear is only about pi and final state. So pi pi can only go to pi pi. So in this region, we don't have to look at anything else. Now, if we were looking above this region, we would have to take a look at all the possible channels that are measuring this or other experiments. And then you can see the plots, right? But you don't have to do that. So if this, I mean, it's a very simple line. It's kind of like a straight line. It goes through the data, it has a good chi-square. And if I go and instead of plotting just the real axis and the value for the phase shift, I plot the modulus of the amplitude in the complex plane. So now, this is the invariant mass. So this is this part here. And this is the imaginary part of this variable. So this is that I extend this variable and I literally continue this variable into the complex plane. And I plot the modulus of it. And this is what you see. This is actually that thing. Okay? So first things first, what is this? Why is this continuous? Aren't you wondering about that? Perhaps you know the answer. The second one is, well, you told us that there are poles close to the real axis. But there are no poles in here. Okay. This, by the way, is the fact that in here, this is a smooth, is called analyticity. And it's the second of the three first principles that I talked about. Let's, in a non-relativistic way, prove this. So let's say that we have an incoming wave packet. So we're going to have our pions, we produce a wave packet that can be different in shape or size, but we are never going to care about the actual function that creates this wave packet, only its basic properties. And we are going to scatter the pions. So we have the incoming wave packet, we send it, then they scatter, and we get an outgoing one. We can mathematically relate the two through the S matrix. Remember, we usually subtract this -1 means the trivial non-interacting part of the S matrix. So we take it out, we get this part, and this produces a relation between the outgoing wave packet and the incoming one through a function. I don't know the explicit value of this function. I don't know its algebraic value. This is QCD. I don't know. But let's take a look at something very simple. Do you think that in an experiment, when you detect pions at the end of the day, they are going to show up before you send the beam? So you didn't switch on the machine, but then you start getting pions in your chamber. And that would be awesome. And then neutrinos, end up flying faster than light. But it doesn't happen. In any theory that we know that makes sense, the theory must be causal, right? Things happen, like the consequence happens after the cause. And so it means for us that t, which is a final value, must be always greater than t prime if we want to get something. Or this function must be always 0 if t prime is greater than t, because it cannot produce any effect if it doesn't happen yet, right? So this capital G function, which value I don't know, related to G's little g, looks like this, just because of causality. Okay, still, we don't know the explicit value for this, but we know it must be causal, it must be well behaved. So because this capital G function that is going to relate the scattering, the outgoing wave packet with the incoming one, looks like this from 0 to infinity because of causality. Now in the upper part of the energy plane, let's say that we're describing everything in terms of the energy, in the upper part of the complex energy plane, what do we get? We get a real value for the energy, right? Plus I something. Now, this exponential, I times I, is a minus, right? So in the upper part of the complex energy plane, we could get a decaying exponential here on the integral, which makes everything converge. So this function is well behaved, and so scattering in the upper part of the E plane is well behaved. There are no poles. Now, if you live in the lower part, this will be a different story, because we will recover an exponential that grows. And so this integral will be well defined. But let's say that we're only in the upper part of the energy plane. Now, I squared it. Where does the upper part of the energy plane go to? When you have the phase of a complex value and you square the whole thing, this becomes twice the phase, right? So the upper part of an energy plane from 0 to 180 becomes from 0 to 360. So in the E square variable, which is what we call S, right? Is the Mandelstam invariant, is E squared. the function is well defined, well behaved in the whole context. And this would be just, there are no poles there. Okay, what are the poles? I promise you there are. Where are they? Well, first things first, what is this jump? I keep plotting modulus of amplitudes, and they all have this jump between plus I epsilon and minus I epsilon. Well, this comes out of what we call the spar reflection principle. It's a mathematical theorem. I'm not going to prove it. It's not very complicated. But the idea is that if you have a complex function that is well behaved, and has some real values in the real axis somewhere, then this relation always holds. We just prove that our functions are well behaved. So they do respect this principle. Either S or little t. We don't care. So now, why do we have this jump? Well, this jump is just the difference between t of s plus I epsilon, right? Minus t of s minus I epsilon. That is the definition. And this, by the spar reflection principle, is just t of s plus I epsilon minus t conjugate of s plus I epsilon. What is this? This is just 2i, the imaginary part of t, right? The function minus its complex conjugate is just 2 times I, the imaginary part. So wherever we have an imaginary part for the function, we have a jump. The greater this imaginary part, the greater the jump. Okay? Very simple. You played with this action for years. The square root function in the complex plane has this. I don't know if you were introduced to them, but you should have. They are called multivariate functions in complex analysis. You were introduced to the square root, you were introduced to the logarithm. All of them have these branch cuts. Whenever a well-defined function in the complex plane has an imaginary part, and this is why I'm plotting here square root of minus s, or minus x if you want, then it will have a jump. Because if you look at the faces above, then this will have no face. You will look at the face at 360 degrees, is this, right? So one is I, the other is minus I. What is the jump? Is 2 times the imaginary part. So at x equals 1, this is just 2 times I, right? It works. And this creates a complicated structure of what we call Riemann surfaces. So basically, the idea here is we have the square root function. Now we just discovered that it has a jump. And then you ask me, hey, what happens if I go in this direction? I want to continuously go in this direction, or I want to go continuously in this other direction. Well, you end up getting something like this. And this is the square root. This is beautiful. If you go in this direction, it's going up here. Keep going, well, and you connect continuously to this other that comes into and enters into this one. You see? So the two Riemann surfaces in here are connected. So this function has a two-sheeted Riemann structure, 2 sheets. The first sheet is the one where you define everything, and the second one is hidden, that you can also calculate. And this is where the poles live. Okay? By the way, this is also a proof of the optical theorem. As unitarity tell us this, right? We define this for the t function. But now we just calculated that t minus t dagger is equal to the imaginary part, 2 times I the imaginary part. So basically, this is equal to the sum over all possible scattering effects, which is the cross section. You know. So whenever in an experiment we measure data, there is some scattering, then the imaginary part is different from 0. And so we have this. So first, see the structure is clear through poles. You define, you feed the data. This everything is very clear. And now you go directly through this. Boom, you have a pole. This is the signal results. So there is a state here, there's a pole. And you see, the line shape of this doesn't look anything like we were seeing before. If you are playing with bright linears, this doesn't look at all like the simple parameterizations, but there is a state over there. So, well, because I'm running out of time, we're gonna skip some other details, but so let's say we can get, and we can play with this after the classes or, you know, as an exercise, we can get an explicit way of going from the first sheet to the second one. So it makes everything very simple, because if we know the parameterization to the fit in the data, then we know how to handle poles algebraically. Okay? So any questions here? If you don't have something very relevant, no, it's better maybe to do it at the end because I'm running out of time. But if you have something urgent, yeah, just scared you enough. So now this is more dense. I'm sure of that. So let's play with what we just learned. Okay, so this is going to be simple. We're going back to play the school plots, no maths. Well, mostly no maths. Remember the quark model? Maybe you remember that we calculated the possible quantum numbers for a quark and an anti-quark for mesons, right? Are given in this table. You saw them on Wednesday. So do you see a 1 minus plus in this table? No, you do not. So I was asked on Wednesday to explain why was I calling this 1 minus plus hybrid. And so the idea could be something like, we are just going to revert one of these particles of the 1 plus plus by including a gluon. This is going to revert the part. However, when you see a theoretical predictions coming from models or from lattice QCD, you see a prediction of one single hybrid state. If you go to the PDG, to the book, then you see two. But this is very problematic because it means that we are not understanding anything, right? So we're saying that we do this to understand QCD, to gather information. Turns out we just go over the corner and we got everything wrong. So let's take a look at those states. So we are going to use a fantastic experiment called MASS at CERN. So they use very highly energetic beams, ion beams. And let's see what they measure. First things first. This hybrid, as I said, is 1 minus plus in JPC. Let's start to take a look at the possible lightless states. So can it decay to pi k? It doesn't have a strangeness, so it cannot decay to pi k. Can it decay to pi pi? Well, these are the changes in quantum numbers of pions. And then if you combine them, because they are identical particles, you have to symmetrize and symmetrize according to the rules. It means that we do not have that final state in pions. So no, the hybrid cannot decay to 2 pions. But it can decay to a pion and an eta, or a pion and an eta prime. We also played with this, because they are no longer identical particles. So this is a way of describing the system. And yeah, we get a moment. Yeah.
In final states with multiple particles, do we need to be concerned about the relative orbital angular momenta between them?
For which specific?
In terms of the possible final J states that they can produce.
Well, so the idea here, of course, is that the total angular momentum of this object, right, is 1. It has spin 1. So if you have 2 pions, they don't have a spin. So you will have to have a state where the 2 pions combine with a unit of angular momentum to create this J equal 1, right? And that means something on the permutation relation because they are identical particles, right? This is exciting how you don't get that number. Because the point here is that pions and etas have the same quantum numbers. The final state is different just because one you have to combine in a specific way depending on the angular momentum that they have it, the orbital one, and the other one does not. Yeah.
In that case, is it accurate to say that if we had even like a 3-body decay, we wouldn't be able to make a statement about the distribution of those angular momenta?
Yeah, it's very complicated for a 3-body decay, right? Because whatever you recombine on 2-body final state will be also recombined with a third one. So there are many possible ways of getting the same J, where 2 of the systems can have like a tower of partial waves. So I'd say, as a rule of thumb, it's going to be very complicated to just state what is the exact set of angular momentums on each one of the 2 invariant systems. Right? You can do 3 permutations, so it's going to be complicated. I mean, still, sometimes you can do. So there are some cases we can talk about that later. We're more or less can guess it. So let's take a look at this. So we have the experiment. It's a very nice experiment, relatively new. It collected lots of data and it has very nice kinematics for us. 1 minus plus, so eta pi or eta prime pi final state, and these are the invariant masses. So this was measured. These are data from the experiment published. What do you see? Well, we see 2 peaks, and they are not at the same mass. So one of these peaks is roughly 1.3, 1.4. The other is roughly 1.8. And this is what motivates, well, because it was also seen in other experiments, the plea to claim that there are two states. But as I said, this basically is telling us that we didn't understand anything here, because all theoretical predictions and lattice QCD predictions said that there was only one state. So who is wrong? Is the experiment wrong? Is the theoretical expectation wrong? Is something else that we are doing that is sloppy? It's gotta be this one. So remember the definition of intensities? I told you that they are proportional to these spherical harmonics. And then we can see it here in the data. So this is the amplitude, not the partial prediction. Eta pi final state, eta prime pi final state, and this is the cosine of this theta. What do you see here? Is it this kind of, you remember when you are looking at chemical orbital potentials, these different shapes and sizes and the geometries, right? If you take a look at this, you have accumulation of events in here and over there, symmetric. It's zero, and it's also zero in the corners. So this is equal to J equal to. So this is dominated by a tensor group. If you just calculate these spherical harmonics, you will see that this particular one has this expression, which describes very well the amount of events that you see. These are just hits in the detector. But this is what we are counting, right? We're looking for this eta pi in the final state, and we are counting each one of them, or plotting wherever they hit. So this system is dominated by a J equal to, by a tensor resonance. This is not the one we care about, right? We care about something that has J equal 1. Well, the second one, eta prime pi, looks like a combination of this function and this other function. So there is both a tensor, so there is both, sorry, a tensor and a vector in eta prime pi. This is the angular momentum we care about, J equal 1. Okay, so maybe this is pointing to the fact that eta prime pi is going to be dominant, even though, you remember, the phase space to eta pi is greater because it's lighter. So your rules of thumb implicitly of all these points. Now, I was going to say bonus points for whoever tells me this m equal plus minus 1. Why does it dominate so hard instead of other projections? And I thought that you don't know all of this, but you do know all of this because they told me Matt introduced the Pomeron. So this is a Pomeron exchange, and this is what is driving these projections to be plus minus 1. The idea is this is the total reaction that they are measuring. Okay. Now this vertex is very simple. We're going to forget about that. This is a constant. Okay. This is the reaction we tell. How do we describe it? If we invoke unitarity, then we know the unitarity for the scattering part. So eta pi going to eta pi is equal to rho, whenever I put here a loop with some dash vertical line, this means rho, and t times t complex conjugate, or the modulus of t squared. That is the unitarity that we know about, and I'm just doing a diagram to represent. What is the unitarity for this diagram? Well, kind of the same. We have the diagram again, in initial state, then the loop with the vertical dash line, and then re-scattering at the end. So this is the form. Rho, A, and T complex conjugate. Knowing this, we can know the formula for the amplitude. So this is the amplitude that is going to describe what they measure in the experiment. Now, remember that D can be described with numerator equal 1. We can always do that, as I said before. We can always put everything in the denominator. But now, because we have a term that is like a production term, we're going to have something different. Typically, you would assume at first order that this is a constant. And because it's not exactly a constant, we are going to put a smooth numerator. So something that varies very little. Actually, we're going to put some parameters and we are going to allow the data to tell us if we are right or not. But we will be right. Now there is a denominator in the formula, which has to be this one. And it's indeed what we are using. So this is the denominator for the scattering part, and this is the denominator for this function. Now, this is identical. As I said, sometimes I use J, sometimes I use QT, QL, because I'm lazy. And this part, let's forget about that first. We are going to do it in the next lecture. This is just a fancy way of grading this. Okay? So dispersion relation. We're going to talk about those in the next lecture. The idea is, by doing the same for the denominator that we do for the scattering, by just plugging in and grade, we're able to describe the data very, very well for several partial ways and several final states. So we are describing the two peaks now, and this was a field of ours. And you see that the formula that we're using describes the two peaks. Another question is, did you find two particles? The answer is no. We found just one. When you go to the complex plane, to the second Riemann field where the poles live, turns out this guy is this guy. So there is one pole that is decaying slightly differently to the two channels and producing two peaks. And this not only reconciles all the theoretical predictions, lattice predictions with data, but it's also kind of a way of saying, look, we must start doing something more elaborated for spectroscopy, or otherwise we will be fighting over these peaks producing weird things for years. This controversy actually lasts for around 20 years. So it wasn't something for like a few months. Now, it was soon after confirmed by some experimentalists. You might know the name of one of the organizers here. And then it was also soon after confirmed by our lattice collaboration in here, the lattice spectroscopy collaboration. We can also do this for other reactions, and I ran out of time, so finishing right now. We can do it for other very complicated reactions. For example, one of them is the mighty Glueball. If we look at the Glueball channel, and we are looking for reactions that can produce Glueballs, this is a fantastic. Now, somebody will tell me, hey, look, you told us on Wednesday that Glueballs are suppressed over other things. Why are we looking at this now? Well, if you find a way of connecting a CC-bar object like the jet side to pions and kaons through continuous quark lines and QCD, well, then give us a call. Otherwise, it must be connected through something else. So in this case, we are looking at a CC-bar object going to light quarks, so it must be connected through gluons. And this is the cool thing, because it must be connected through gluons in this vertex. Whatever particle arises there must be a Glueball, right? If there was only one particle that appears here, it just connects to Glueballs. It must be the Glueball. So this is what we call the golden channel for the Glueball search. And indeed, we can feed that data very well with these customary parameterizations that I introduced today. You see here all these resonances that we were talking about. This was actually the channel that we were looking at. And the interesting one is this one in the middle. That is the KK bar channel. That's a huge. So basically, by doing analysis like this, you can find these faults in the complex. Many different particles. So I promise you, there are 4 particles interacting here. So it's highly non-trivial, but still, we can find it with precision and robustness. But we can also tell you that this object that we talked about on Wednesday for a brief moment, it is called the 1710. It's a predominant Glueball. It couples to gluons much more than the others. Now, this has been debated also for many years, and it's always been expected to be the Glueball because if you use a quark model, it predicts the non-net, right? But there is a 10th state here, which is this one. That cannot be predicted by the quark model. And so many people have been working on this for many years, but this is one of the most robust extractions of its coupling parameters to the gluons. So yeah, we can do analysis like that in amplitude analysis and answer some questions that have been debated for many years. So I'm going to stop here. We'll continue the next one. Questions?
Question, guys?
I see a difference between Wednesday, where we were all like very energetic and it was so very nice. And today, perhaps it was too dense. No questions. Thank you, Jose.
So in Wi-Fi scattering, sometimes people make use of this omnes function to
Yes.
guiding, but so that is only valid, so it cannot be extended to these formats. More similar.
Like these formalisms, you mean coupled channels, or you mean?
Yeah, the K-matrix.
So, okay, so in pi scattering, which is this data we discussed before, what Jose is saying is that there is a formalism for the ones online that didn't hear it. there is a formalism called the omnes formalism, which is a dispersive formalism that is used with great accuracy and success in the elastic region. And he's asking if this can be generalized to a couple channel, like a general framework. And so the answer to that is a bit. So you can do a couple channel omnes analysis. You can. The problem is you need to know with high accuracy all the possible final states in order to do that. If you are able to get all the data on all possible final states, then you can solve couple channel dispersive equation for the omnes. And so you can define a couple channel omnes equation and implement it. Problem is, as you know, yeah, that is not the case for high-pass scattering. Like some of the final states have been never measured. And so if you are missing one single one of them that is relatively irrelevant, then this breaks. So far, I don't know of a formalism that can accommodate missing information on a couple channel omnes function. Also, on an elastic region, the omnes problem is analytic. So you can define the omnes function, multiply by something smooth, and this all analytic. On the elastic region, this must be solved numerically. There is no algebraic solution to the couple channel omnes problem. It's just a numeric solution at the end of the day when you have the dispersive system.
And the use of Roy equation is.
Yeah, that's it's kind of related to the problem. So we are going to talk about Roy equations in the next lecture. Okay. So Roy equations are what we call full dispersive approaches to solving these scattering problems. So we'll see carry lots of problems. And again, if you want to solve them in the complex, in the couple channel region, you can, but you need to know with lots of precision, with accuracy, all the possible final states at once. And then you need to do a full dispersive approach for all the states at once. So in practice, nobody has ever done this. There are ideas. This is very cumbersome.
More questions, guys?
I think for your last slide.
Yeah,
Oh, the other one.
that one?
Yeah, so you mentioned, I mean, you can see on the none there.
Yep.
The F naught 1370. Why is that not showing up in this?
Interesting. Yes, that's a good point. Very good question. So we have the non-net, and for those of you who don't know, the quantum numbers of this data is, for example, this wave is 0++, JPC 0++. This is the same JPC of these three objects here, the F naughts. That's why they are called F naughts, the three of them. They have the same JPC. Okay. So then the question is, if this thing has the same quantum numbers as the other two, why do the other two show up in this plot that I have, but I don't have anything for the 1370 in here? And so we go back to the original reaction. So again, the reaction must be basically driven by two gluons producing pi or kk, right? Which means that we have a vertex in the reaction, this one. So we have a vertex where we are going to have gluons inside that are going to produce these states. So if our resonance doesn't couple to gluons, let's say that its gluon contact is 0, then what is going to be the value for the vertex on that resonance? It's going to be 0, right? Because it doesn't couple to this particular production process. Which means if a resonance has very little coupling to this, we won't be able to see it in data. And as you see in data, there is nothing over there. There is no 1370, neither on pi nor kk. Yeah. So the first one that you see in the first peak is what we call the 1500 here. There.
So on the other hand, we have two other peaks. So what distinguishes the F naught 17?
Yes. So the idea is you can, once you get your parameterization, this one, you can tell me what is the coupling to this, right? Because you fit it to data and you got the poles in the complex plane. So now you can tell me what is the production of each one of these points in the complex plane, which one is the production of vertex of each one of these resonaces. And when doing so, then you see, well, I'm comparing here 1500 and 1710, not the other two. But you see here the dominant one is the 1710. This you can also see in data. Well, yeah, I don't know if you see the numbers, but for example, comparing the 1500 and the 1710, the average is that the 1710 couples almost 10 times to kk, this is kk bar, this is pi bar. So it couples, roughly speaking, 3 point something times more to pi pi, and it couples almost 10 times more to kk bar than the 1500. So that tells you this is clearly more Glueball than the other one. I don't have a plot now for the other two, but yeah. So the idea is we are calculating this production radius, and then it's telling us which one is coupling more to that part. More questions?
At around 1.5, is there a possible other resonance at larger width, or
I mean, this points.
yes?
Yes. So that's another good point. So you see some great points here. So what I'm plotting in this complex plane, this is part of the complex plane. So I'm just plotting the complex plane. And if it's a smooth, I'm not plotting anything. Whenever you see a point, means one of my resamples, not gonna go into details on resampling, but one of my points in resampling the feed to the data produced a point. So on average, everything that you see red was one point, just with the uncertainty. Everything is basically discovering the full uncertainty. Everything you see in blue is one pole, green is another pole, the purple is another. What is this gray collection? So I didn't go through the idea that when you have parameterizations, we don't know the explicit formula, we are just inventing it based on some first principles, right? So let me go to the chemistries. Yes. So now, nothing mathematically tells me, nothing tells me, you cannot prove this, that this thing cannot generate more poles than what I am plugging in inside here. So if I put just one of these terms, naively you are going to expect one resonance, but it can produce many more. And this is simple to see. For example, let's go back to the last two. Okay, this is just a function, pi to pi. And now you are going to describe it like this. How many poles does it have? You know the answer. How many poles does this expansion have when you plug it in here? Whenever you have a complex function in the complex plane, and it's a polynomial of degree capital N, it has n zeros, right? This is basically the idea in the complex plane is that you can always find the zeros of a polynomial of degree n, and it has n. So if I put something of order n to describe my data in the denominator, then I'm always going to have n zeros. No way around it. One of them will be my physical pole, and then the other thing will be artifacts, because I am not good enough at describing the data. So I need more parameters than QCD might predict. It's very complicated, and so I produce these artifacts. Now, this is a big problem, because if those artifacts end up very close to other poles, then they are screwing everything up. You don't really know what's going on. But if they are very far, or if they are not very relevant to your analysis, production, the couplings are very small, then it's not something terrible, right? So when doing this plot that we're discussing, this gray thing is an artifact. Okay, it just is so far from the real axis, and the coupling is so small and appears so few times. Here I have like 200,000 poles collected for a single pole with errors, and here I have like a few hundreds. So basically, it's an artifact, and I am just going to consider that it's not physical resonance because it's not stable. It appears only very few times, and it doesn't really matter.
Question for that.
Oh, okay, nice.
One question, guys, or you don't maybe.
Yeah.
Sorry, if this is kind of a silly question, but when you
Yeah.
were doing the parameterization for K.
Yeah.
Or well, I guess using, or not K, but the I guess in your parameterization where you have like the cotangent of
Yes.
delta. Going back to all that stuff, and you were approximating it using the polynomial.
Yes.
What energy range were you doing that over? Was it just for that low region where the function is kind of increasing there?
So this is the interesting thing. So let's go back to this. So let's say that we start by the naive way of parameterization. You get the full T, and then you put a polynomial over it, right? We have just seen that you cannot describe poles because you use a polynomial denominator, so it has no poles, and it breaks unitarity, which is not. But look at this equation. If the imaginary part is small, or the modulus is small, you are not breaking it much, right? Okay. And if the value is small, then you don't have poles. If you have poles, then you have huge value. So this might work here, and it does work here. Now, what I'm trying to stress is that doesn't matter if you put 1 or 10 parameters, it won't work here. Okay? But it will work very bad, and you will need tons of parameters. Fine. Now, for this one, because it respects unitarity, a small count on this, or basically as not so large degree of this polynomial, will be able to describe data much better. So if you, for example, use few parameters, you will describe this region. But if you use more, you will describe the whole region, because you can generate a point here by using anything else. So in principle, you can describe the full elastic region. Remember, so this is just a function, not a matrix. So you can only use it when you have an elastic region. But you can describe the full elastic region just by using expansions in the cotangent, because you are respecting unitarity.
Although I guess this T is in, so like this T is part of another function, because I just thought like an inverse polynomial was just kind of like monotonically following all this ones.
Well, but remember that you are not expanding the full denominator, you are expanding this part.
Oh,
So
just
you always
that.
have this term that is fixed. This is what gives you unitarity.
Okay.
So basically, the unitarity relation, this one, can be written in a different way. And I didn't mention it because there are too many exercises that I dropped already. But it can be said, so for example, get the inverse of this. So the inverse of T. And then calculate the imaginary part of this. This is real, right? So what is the imaginary part of the inverse of T? Minus I rho, right? So that is the unitary relation. So that is what this I rho is never expanded. If that I rho is there, then everything is unitary by construction. And so is this thing cancellations between this and that can produce the poles. So is this thing, right? If you were only expanding everything in terms of a polynomial in the denominator, then you will also be breaking unitarity.
Sorry, this was just kind of a follow-up question, because you said that you could add more parameters, to try to, describe, further and further on.
Yes.
Yeah. Do you run into issues when you kind of consider, because, I understand like you can approximate, like one of the lower energy regions just using a handful of parameters pretty well, but obviously as you get to, higher, energies like a higher S, it diverges
so yes,
more and more.
Sorry to interrupt you, but just before we go into that, we can describe this full energy region with this expansion with 3 parameters. 2 parameters more or less describes it. 3 is perfect. So it's not that we need 20 for that. Even though this expansion, 3 is perfect for that description. But yes, I mean, the larger the energy region, the more parameters we need.
Because I was just curious if you run into if it like describes it pretty well over that region, or if at some like higher point, because it's a polynomial, you get like a very big divergence from what you would expect.
No, it usually works very well. Yeah, as I said, I mean, the main requirement here is that it's unitary. So if you are respecting it by construction, it will always work well. What is problematic? I mean, many things, but one of the things that makes everything problematic when you have like a large energy region and you need many parameters is, of course, getting the errors right. And you will fit in a huge energy region with lots of parameters, and then they will be highly correlated. And these, minimas are no longer linear; they are highly correlated. And so, if you get the bare errors from a fit, you will end up with something that don't really have don't necessarily describe the honest to God errors. And so this is where resampling comes into play. You might have heard about bootstrapping data. This is what I mean by resampling.
So with these T amplitudes that are describing sort of in this case, a pi to some exotic meson back to pi. How does that correlate back to our DIS experiments where we have electron on proton, which it creates an exotic meson, which then goes to a pi system?
Well, so for example, if that was the reaction, you have a different initial state that then decays to pi at the end of the day, and it's just a scattering. The difference, all there is an inelastic process. So you can describe it with matrices, right? So for example, let's say that you have like something like an experiment that runs on quantum problem. You have product fusion at the end of the day, the quantum numbers, it decays to something like that. It just means that you at least have a 2-to-2 matrix. Because you have that heavier channel coupling to the lighter one, the lighter can rescatter on itself, and the lighter one can also produce the heavier channel if you have enough energy, right? So at least you have a 2-to-2 matrix.
I'm also imagining, though, it might have an impact on the geometric sequence that we use to get to this result, because the first term of the first interaction that occurs, will no longer look like the subsequent terms, because our initial state is not the pi, which continuously separates and recombines.
Well, yeah, but so remember that this is a kind wave introduction. You can still define this as a matrix, and this respects every principle. You can just like the same. Forget about this expansion. But these are matrices already. So this accounts for all possible initial and final states. All I'm saying is whatever drives the interaction in between the initial and the final state is that particle. So let's say that you have something heavy and something light. But you can also have something light to something heavy, something light to something light, or something heavy to something heavy, to something 4-channel, 2-to-2, right? You can describe it with K. All you need is different couplings in this corner and this corner. One coupling per system that you have. So if K is a matrix now, this holds perfect. Because K just has, let's look at the explicit formula, you'll see. K has a coupling. So in every vertex, you have a coupling to channel I, so this can be the heavy one, and a coupling to channel J, so this can be the light one, or vice versa. Or I to I, light to light, or J to J, heavy to heavy. So it accounts for everything. All you have to assume to do this hand-wave expansion, for example, in this case, is that whatever drives the interaction between the two is a quasi-stable state. Doesn't have to be that way. When we do this, when we play with this, we usually call it, Bayer interaction, a beta salpita kernel. Some people here probably work with Dyson singular equations, play with beta salpita kernels. So instead of like having a propagator, you can call it a beta salpita kernel. There's got separation between short distance and long distance interactions. Okay, but it holds if it's a matrix. Now the question that is also interesting, just to elaborate more, is what happens if instead of having scattering to scattering, you have production to scattering. So what happens if not everything is strong? Like you have a pion and a photon gamma going to pi. That is an inelastic direction. But the vertex gamma pi isn't describing QCD. It's another kind of reaction that we consider a production vertex. So in that case, is exactly what we're looking for here for the hybrid. Sorry that I keep switching. But this is the kind of reaction. So this would be pi gamma and then pi here. So this vertex we consider kind of a constant at the first order. And then all the rescattering effects and the K matrices happening here. So that is why this as a function will have a term in the numerator that is something smooth times the denominator of the scattering. So this inverse of K minus I.
Okay, well, I would suggest that we stop here and go to a break. And we see you in 50 minutes. Let's send a catch.
Testing.
Well, welcome back to our morning session. Now, Arkaitz, the floor is yours for lecture.
Thank you, Juan. Okay, welcome back, everybody. See, not many of you escaped, so wasn't that bad. So this is the very last lecture. So first couple lectures were like introduction to particles, the ones that I care about the most, mesons. We haven't talked about variance. And then we've been playing with things that we define with the quantum numbers, like these amplitudes, and I introduce you a customary way of describing. Now we're gonna go, I'm gonna up the notch a little. We're gonna go into the fancy analysis. What is the best of the best that we can do for these scattering processes? Can we get fully model independent results for these amplitudes? Can we get something that is once and for all, and we don't have to fight about using this or that model to describe the data? We're going to take a look at the light scalars. So I introduced them on Wednesday, and the idea is very simple. We have these non-nets motivated by the quark model. We have all the symmetries, right? The symmetries. And so if we have SU3, then we are going to have 9 states, 8 plus 1, octet plus singlet. Naively, if I knew nothing about particle physics, and then you introduce me the light scalars, I'd say this must be the simplest case. So we introduce the pseudo-scalar mesons, and then this arises as a result of the scattering from the pseudo-scalar mesons. So these are like the vectors, like the omega, the rho, the phi, only they don't have angular momentum, they don't have a spin. So if I ask you which one is going to be simpler, something with a spin or something without spin, you're going to say, oh, something without spin, right? These guys. Well, turns out they don't look anything like the shapes that we like, the Frey-Wiener shapes that we like. And their compositeness is also something that hasn't been answered for many years. We only have partial model-dependent answers, but we don't really know if they are tetrachords. We think that they might be more molecules. And there are some people that think some of these states might have some Glueball components. So let's see how we describe, how do we go from errors this large for the parameters to something much more precise. So first things first, you want to describe a state. You want to tell me what this is made of. You want to understand QCD. Well, you go and describe it with precision. Otherwise, we are not going to go far from that, right? Well, turns out this is the past error value for the kappa state. So yeah, not very precise. This is what the PDG said about this state back in the day, 1967, where it was compared to some cool things like the Loch Ness Monster and the Abominable Snowman. And well, again, this is not needed. It's ordered, you can see it. And so we're going to explain how to go from this to that. Okay. Now, not only that, we can also determine things like this scattering length that we were playing with before. And there is some controversy there between lattice QCD driven values and our dispersion results. So we will say just a few words on that. The big problem, because there are two big problems with these scattering processes. So first big problem, all these light scalars depend on many complicated analytic structures. So I introduced to you this branch cut thing that happens when data exists. This is basically the threshold of the reaction for pi k scattering, and this is the real axis. And this is the physical region where data exists, right? So you feed data here, and then you want to get poles. The k star, one of the vectors, lives very close to the data. So, okay, this is a short trip. You can do it by walking distance, and it's fine. You get a k star. And now the kappa lives here. It's very far from data. Data is to the right of kappa. But to the left, there is a whole layer of things that we cannot describe with data because they are not in the physical region, but they are there. We can prove it analytically. So if you want to describe some of these states, well, you are not only going to need data, but you are also going to need the low energy expansion region, which is below threshold, something that is called the Adler field that we won't describe, you might know about, and what we call the left-hand cut, which is very complicated, right? It has a circle and everything. and this complicated structure. Otherwise, you won't be able to go to this pole with precision. If you do use models for this that don't account for all these low energy regions, then you will end up with a stress issues. And this was debated for 50 years from the sigma. So, it's not very good. And this is something that we also see on the lattice nowadays, because the lighter the pion mass, the more these things are relevant. Because in lattice QCD, the masses of the pions are usually, well, back in the day, they were very heavy. So this thing is pushed to the right. But let's say this thing and this thing are farther apart, okay? But the lighter the pion mass, the closer these two are. So the more relevant it becomes. And this produces slabs and circles. This is just one of the problems, which is the analyticity problem. There is another problem, which is the experimental problem. And if you remember that all these measures decay, not under the strong force, but they do decay. So they live for some meters. That's fine, we can play with one of them, but playing with two of them is complicated. Because if you have a big accelerator and you start with two beams that are farther apart, at the end of the day, what you collide is vacuum. So you miss them, and you no longer have two measurements. And this means that data is not data. Data has to be modeled from indirect measurements. Like, for example, this thing. So you have one measurement beam that you can play with, just one, and then you make it collide a target. In this case, a prototype. That you can assume some point in some kinematical region that this thing is mediated by a pion as a virtual particle. Okay, this is not a real pion; it's a virtual particle. If you have a good model and the kinematics are perfect, okay, it's not terrible, but this is still a model reaction. So data is not data, and this ends up producing errors this large in the data. And some systematics are neglected because we do not understand them. So yeah, we have to be proactive here. So the solution is this. The solution is to invoke all these first principles. You've been introduced to unitary analysis in the previous lecture, and we're going to speak now about crossing, and how the three of them together can give us the right answer in this reaction, and so on. Okay, so what is crossing? Again, have these states that are influenced by the data on the right-hand cut and something that is called an effect. Crossing is the relation between particles and antiparticles. So we are going to cross a particle and antiparticle. In case of pi pi to pi pi, right? The antiparticle of a pion is a pion cell. So yes, they are related. If you cross pi pi to pi pi, you get again pi pi to pi pi. And the mass is a mathematical relation. This is a mathematical relation. We can define one amplitude, one analytic amplitude, and unitary amplitude, with respect to entirety, that describes all possible process depending on its variables, its understand variables S, T, and U. So let's take a deeper look. This is what we call the direct channel. The data lives in the direct channel, what we can play with in the physical mode. And this is going to be called the cross channel. This is going to be produced by antiparticles. Okay? So as I said, we have one single amplitude that describes all these processes. I'm not going to prove that. It's not trivial. But we can take a look at what I mean by that. So let's say that I have one process, 1, 2, 2, 3, 4. So pi, 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 pi. And this process is above the S channel threshold. So pions are interacting. It's in the physical. This is the S channel process. 1, 2, 2, 3, 4. Fine. Let's say that I have one anti-3 to anti-2, 4. So pi, pi to pi, pi. But now the energy that is greater than the threshold is the T channel energy. This can be plotted like this. One anti-3 to anti-2, 4. Okay? This is another reaction, but they must be related through the variables. The third one is 1 anti-4 going to 3 anti-2. So now pi, pi to pi, pi. Yes, the understand variable that drives everything now is U. And this is depicted in this one. 1 anti-4 to 3 anti-2. So yes, we have 3 amplitudes, right, for this process, permutations. And the 3 of them, are physical in these regions. Well, let's say that I put some conditionals, and I call this capital T the combination of these three with some conditions. And in the middle, it's going to be something that goes analytically from one to the other. So we analytically continue this T, not only in these regions, but also outside those regions, to describe the full S, T, and U variables in the dimensional description. This is the whole connection. And so this is what we want. This is called the Mandel-Stahl hypothesis. Okay, or hypothesis, because there is no mathematical proof. You can get some decent skeleton expansion and description of this. I can point you to the book if you want. It's not true. Now, what are we going to do with this? So we are going to build here our own dispersion relation. I don't know if you have ever heard about dispersion relations, but they exist everywhere, and you have actually played with them. You want to solve a harmonic oscillator, and then you introduce a random force in the harmonic oscillator. You're going to solve a dispersion. When I play with optics, the whole line propagates over different mediums. We're going to play with dispersion relations. When I solve quantum mechanics and some non-ordinary potentials, you're going to play with dispersion relations. And the same in quantum field theory. Okay? But yes, we know what's the analytic structure of the amplitude. Let's simplify. You remember that we had some complicated circular left-hand cut and some simple right-hand cut. So let's start with a capital P function that has a very simple structure, much simpler than the puzzle. It's just straight lines to the right and to the left. Okay? Because it has cuts here. These cuts, remember, are the discontinuity jump of the produced by the imaginary parts, right? So we can go below and above them and have a path like this. And now the amplitude is analytic inside because we proved analyticity. So we can invoke the Cauchy theorem. You probably have played with it. Fine. So we have everything, and now we're going to assume that this path, that is going to go to infinity, is negligible because my amplitude decays very quickly. If not, we have to do something else. But let's start by assuming that, okay? This part is going to be negligible, and it means that we are going to have to care about the continuous paths. So it's going to look like this. This is going to be where data is, and this is the left hand. Wait, I'm going too fast. Why an imaginary path? Went from T to an imaginary path. Well, you can see it here. Let's get this right part. You have an integral that runs below the cut in the negative direction, and then a part that goes along the cut on the positive direction, plus a epsilon. So this is basically T of S prime plus a epsilon. S prime because I'm going to integrate on it, okay? That's why I'm using the prime variables. Minus P of S prime minus I epsilon, because it goes in the negative direction. And we proved this in the previous lecture. This 2i times the imaginary part on S prime plus H. We just proved. So yeah, imaginary part. This 2i is going to cancel the 2i in the denominator of the Cauchy theorem, and then we just recover that 1 over 2. What is the analytic formula, the right formula for this left hand? Well, let's look something like that. Now, let's simplify everything. Just pi pi. Same as pi pi to pi pi, same as 4m pi squared. Okay? Just to calculate our first dispersion relation explicitly. So this is how the right cut red looks like for data listing. And we are defining the plus I epsilon on top of it. Okay, it's a limit on top of it. And this is where the left hand cut blue looks like. And we define the plus, we define a minus I epsilon below. This is convention, but I'm defining it that way to make things simple with signs. Now, the problem is data lives in here, but there is nothing over there. So we know nothing about that integral. We cannot calculate it. So let's do magic. Let's relate that cut to the right-hand cut by using crossing. Now you'll see why it's so relevant. First, we're going to change the variables in this integral from S prime to something like this. As I do the algebra, you recover this expression. Now this U prime is a dummy variable, right? I could call it U prime, I could call it L or C, whatever. It's just integrated, and we know what this is. Now this integral looks like a right-hand cut. So we went from something on the right-hand cut plus something on the left-hand cut to something on the right-hand cut, yes, just on the right-hand, right? Okay, we still have this weird thing. Now, remember that the three Mandel-Stahl variables are related, because ST and U give us a relation, right? Have you proved it? It was homework. Now the idea is I am explicitly writing the third variable here, even though I usually don't, because we don't need it. Just to do the last relation. The last relation is to involve crossing. Crossing basically is going to tell us how the amplitude looks on this STM and relate it mathematically with U, T, and S. You can also do it with T, S, and U. That's no problem. You just have different matrices here that makes everything. And those matrices you can calculate algebraically. They are basically transformation between Clebsch-Gordan coefficients. So matrices that relate different Clebsch-Gordan coefficients. Okay? Not very complicated. So this was our formula. And now this term in here is just going to be rotated from S and U to U and S. Remember that U prime now is a dummy variable. So I can very well call it just S prime. So S prime, S prime. And when I rotate U prime to this side, S prime again. And that is the final formula. Yep.
If we wanted to consider additional possible final states, would we then?
We'll go to that. But so the idea is that in an experiment, you can always tell me which final state you want, right? So this is pi pi going to pi pi. There will be other final states, right? But this formula still holds because it's pi pi to pi pi. Now, the channels will be here, okay? The elasticity for this link to other channels will be included here. We will go through that.
So then does this refer to components of the T matrix, which it corresponds to all possible decays?
No, so this is only pi pi to pi pi.
Okay.
So this is will be just the entry pi pi to pi pi.
Thank you.
Not in general entry. So this will be just one entry. Okay, everything clear to this point? So what we did at the end of the day is we have an integral equation that is written just in terms of data. Now we can solve this, right? We have data, we can get this, and then we can calculate this with the integral equation. And this is what we are going to do. Now, the structure for a parcel for these little t's is a bit more complicated, more cumbersome, not more complicated. Because you know what's the algorithm, what you want to do, it's not impossible. Problem is, we have this circular cut for the parcels. So everything is mixed in a weirder way and the formulas are longer, but the same. The algorithm is something else. So you can get an integral equation that only depends on it. What is the path? The path towards a model independent analysis. The path toward model independent analysis is to impose the three matrix principles in this reaction: unitarity and analyticity that we already knew about, and finally crossing. When you invoke the three of them, you can get integral equations like this. Okay? So what we have to do, this is our recipe. First, we have to use all the data available, because as I said, data is not perfect. We want to be as close to perfection as possible. So we get the data, we feed the little t's, the parse waves, and then with that we recover the amplitude. Versus the second one would be what? Some data we know is obviously grown. Sorry to say, but yeah, some data has some systematic uncertainties that are not very well understood, and some others have like large uncertainties. So you might as well not use it because it doesn't tell you anything. Remember, some of these experiments are very old. So you can prune, and then you have to feed the data. The third one is obtain your favorite dispersion relations. This is the simplest one that you can get, and you can go, to something way more elaborate. And the final one is green and red. So feed to the data and dispersive output, so solution of the integral equation, must be compatible. Because if they are not, then you are violating crossing. So you no longer describe the three first principles, right? So let's go through it. We are going to play with pi case scattering, which is my favorite chunk. For pi case scattering, instead of pi pi, the equations are more complicated. So in order to simplify, I'm going to just put t for the Mandelstam variables, right? The one that is here, equal to 0. So it's no longer a variable, it's just a variable. Second thing is, in the literature for that, we decided for no good reason, I think, use F, capital F instead of capital T. So now I'm going to call it F instead of T, and little f instead of little t. Okay? We can describe little f as we did before. So if you have data on pi k, you can use this formula in the elastic region with an expansion like the ones we were discussing. And in the elastic region, we can do all of this, but we can still describe it. And what we care about is this channel. the channel that goes from pi k to the kappa resonance back to pi k. Does anybody know what is the isospin of that channel? It's 1/2. So what is this thing? I mean, we forgot about isospins, but they are relevant. We have pi k scattering. So which are the isospins? Well, I mean, they are here, so you can read them. But yes, what is the isospin of a pi? What? And the isospin of a kn? 1/2. So what is the possible combinations? 1/2 and 3/2. Okay. So this means that we have two different amplitudes. In blue, I can, I can rotate the bases. I can do some mixes. That's no problem. The idea is that I'm choosing these definitions of my amplitudes, which is a combination of isospins, because they're very convenient. And they are related to the green amplitudes, capital J, capital G, sorry. The green functions is crossing. Remember, crossing is going to relate, for example, 1, 2, 3, 4 to 1 anti-3, 1 anti-2, 4. What is that? That is pi to k bar, right? So the cross channel of pi k to pi k is either pi k to pi k or pi to k bar. So we want to describe everything, we need to fit the two channels. Fine, we can do that. These are the definition of the partial waves. You give me data here, I describe the amplitudes and then my dispersive result. So this is how data looks like. Okay, use all possible data. As you see, it's messy. And as I said, some of this data are wrong. We can prove it that it's wrong. Otherwise, we will use as much data as possible. Some other data, you include it in the fit, but they have huge uncertainties. So at the end of the day, it's like you didn't include it, right? How do you fit it? By minimizing the likelihood, which is a chi-square fit, right? Which has the errors on the denominator. So if the error is huge, the weight of that data point is 0 basically to our likelihood. Most of it, this data was produced in the 80s. This is still the best data we have of today. And we will run a new experiment at Jefferson Lab in a few years. That is going to measure this, hopefully with more precision and less systematics. Now let's prune it and fit it. So I'm showing you the most precise data for some scalar waves from different isospins. The important thing here is that all those fits that you see here were done with something this simple. I promise that it's simple yet powerful, and indeed you see some explicit fits that we did with that formula. So it works. And so we have now our fits. We have our partial wave and our amplitudes. And our idea is that we have to choose our dispersion relations. They are not that simple for pi k. And as I said, they are much more complicated for partial waves. But the thing is this. So let's say that you start from a capital F and then you project to a little f and you get your dispersion relation. Now, these k functions and capital G functions that I have in the integrants are algebraic. We know the answer algebraically. They are not trivial, but we know we don't need to write it. These are the fits to the data. And the same for the cross channel. There's a complicated dispersion relation, but in colors, green is pi to k bar, blue is pi k to pi k. So you see, if you fit the data, you can get this dispersive answer. So you have a system of integral equations. And you can solve that if you have a description of your data. Now, you can prove that this result, this dispersive result, is unique if you do it properly. So we impose the 3 first principles, we get some data, and we constrain the 3 first principles, and at the end of the day, the result is unique. And this is what we consider a model-independent description of the parcels. Okay? If you were to use a different model, quote unquote, to describe your data, and you impose dispersion relations, you will always end up with the same result because it's unique. So it doesn't really matter which model do you use to describe the partial waves. If you describe the data and you do this, then at the end of the day, the result is just one. This is why we call model independent. So the problem is we have to make the input and output compatible, and they are not by definition. So you feed the data, you calculate the integral equation, and then you look at the two of them, and you are like, oh, These curves must be identical, but they are far from identical. These are the left parts. The three different colors mean three different integral equations for each parcel that we are caring about in this plot. And you see, the black line, the continuous black line, is the field. They are definitely not compatible with the straight lines. So we are violating something. In this case, we are violating what is called crossing. And we have to somehow make them compatible, because otherwise we don't have a model independent result. But this is evidence. If I was to describe the data with different models, we will get different answers. So it's model dependent. But we can impose them. We know how to. The idea is just to vary the fits to the data a little bit. We vary the fits to the data a little bit, so they still describe the data, roughly speaking. And then we can recover something where everything is perfectly compatible with the uncertainties. You can see the new fits to the data to the right with the gray bands, uncertainty bands. So it's still perfect. I mean, the chi-square is like 1.5, something like that, on average, something very close to perfection. But we are describing all the first principles. And so no matter which model we use to parameterize this data, we end up with the same solution. So finally, we got our full recipe. So we got our dish, and we did all these steps to get it. Now that we have it, we can calculate stuff. So we not only have model-independent descriptions of the amplitudes, we can calculate observables in here. Like for example, the scattering lengths. The scattering lengths, as I said, are very relevant. Some of you might work at some point or already working on chiral perturbation theory on lattice QCD at low energy scales. And so these scattering lengths are crucial to our understanding of the chiral symmetry breaking pattern and how chiral perturbation theory works. So the idea is, if you calculate this with dispersion relations with a model independent result, then you get these blue elements. Then you have this purple band, which is in the background, this green band on top of a purple one, which are all coinciding to this same region, which are different dispersive calculations of these scattering that we did. So this is what we consider a model independent result with a good assessment of the uncertainty. Now, look at these three green dots in here. Sorry, right? They are clearly incompatible, right? Those are lattice QCD driven results. We know more or less why they are incompatible, but the idea is that by doing calculations like this, you can answer questions that are debated for many years otherwise. This was debated for many years, and the kappa resonance has been debated for over 50 years. And the good thing is, by doing these dispersive approaches, we went from an error that looks like this, and from the PDG not accepting the kappa resonance in the booklet, to an error that looks like that, at least in our determination. Now, PDG will probably put new bigger errors to have a conservative estimate, but this is what we predict. And the idea is that it's not only a model independent result, but to the point that we included all the systematics that we knew about, otherwise we should have propagated more errors. We think that we did a good job, that we did. This is slightly larger than that. But the second thing is that it's very precise, right? Many quote unquote models trying to describe this state are less precise than this result. And you should never just pick one model, because usually models are very deviated from the true solution. In particular for these states that are very complicated. So, this is not the only application to a scattering system that includes dispersion relations. This is just one of many. This is the one that we did recently, like less than 2 years ago. But you have others for pi in the past, which solved the same kind of troublesome case, which was the sigma instead of the kappa resonance. How precise the sigma is. And this is crucial because the sigma, for example, enters in many other possible reactions, and pi is one of the states that populates the most final states in accelerators. So if you don't solve it, then you cannot move forward. We also have answers for pi nucleus, the dispersion relations, and this relates to the pi nucleus sigma term, which is an observable, which is crucial to, for example, searches for dark matter, and also explains to you how does the mass of the nucleus depend on the mass of the transport, for example. And we even have dispersive solutions for E plus minus, which is the way of calculating contributions to the hadron vacuum polarization. And when you hear in the news newspaper or wherever, that there is a 4.2 sigma deviation between the theoretical expectations and the experimental prediction. That theoretical expectation, that theoretical prediction was calculated through the dispersive solution of the sigma. Okay, so it's not exactly what we did here, but very similar approach. That is what is driving these results and this tension. So if you ever claim to be above the 5 sigmas and there is beyond standard model physics, then what you have to do is take a look at these dispersive results. So pretty much what we did here. So well, did you like it? Join us.
Yeah.
We have 2 collaborations in Jefferson Lab that work on spectroscopy and disamplitude analysis. And so I'm going to introduce to you the wall of JPAC Physics, the Joint Physics Analysis Center. If you want to work with us, we're going to be taking a look at all the possible hybrids. Interesting. We have a measurement from Best Street that claims to have found the partner of the pi one that we've been discussing today. But hey, there should be 2 hybrids, not 1. What happened here? One of them disappeared. I'll take a look at it. You want to do XYZ exotics? We might be able to answer those in a few years experimentally at Jefferson. If we do the upgrade, we will measure production of those XYZ exotics we get. Also in the EIC program, when the EIC is built. You want to say something about machine learning applied to exotics? We are working on that. We have results for pentaquark searches, tetraquark searches. But we want to develop 3-body formalism that we need to use now for more complicated reactions than just 2 to 2, right? Have you wondered why did I spend a few hours just talking about 2 to 2? You can have an infinite amount of particles in the final state. Yeah, and many others. You want to work on lattice QCD with us? Well, we're working on lots of projects. For example, somebody could ask, and then I should answer. What do we want to do at the end of the day? We get these states, we calculate the masses, and we put them in a table. Is this all we want? No, we want to understand what they are made of, right? So we want to see inside those states. Well, even use some photons to see something. So we can do that on the lattice nowadays. We have many possible reactions that we can study. If you have, for example, pi gamma by pi. Want to see what some of these F nodes and A nodes are made of? What is their flavor content? We can do that. You want to know the charge radius? You can insert a photon now inside a resonance and tell me what the charge radius is. Maybe one day we can insert this. What is this? Which current is this? This is a HUGS. This is a scalar current. And you answer what is the mass radius of a resonance? Unfortunately, not yet. Hopefully. And we can only do other reactions and calculate every exotics. So yeah, if you like it, of course.
Questions for Arkaitz?
Is there any additional physics contained in subtraction terms when you relate, say, like the real and imaginary parts of these distributions that you're calculating?
Good one. Very good question. And, so, for example, here.
Yeah, exactly.
So what Andrew?
Yes.
So what Andrew is asking me, and for everybody, is if there is some physics inside terms like this. I think is this the question?
Yeah, I think so.
So I didn't go through this, of course. This is called a subtracted dispersion function. This is different from the ones we were playing with before. We looked at that because you don't have subtraction term. So we introduce a subtraction and a dispersion relation when the asymptotic limit of these amplitudes doesn't go to 0 as fast as it should to neglect this certain point. Doesn't, then we can suppress, with an extra power of S prime by introducing a subtraction. You can put as many terms as you want. You can put 10, 100, if you needed them to be. You don't need them to be. There are theorems that tell you that, roughly speaking, 2 subtractions are always more than necessary for all these reactions. But in principle, you could put as many as well. When you put a subtraction, when you want an extra order of S prime minus something in the denominator, you're going to recover an amplitude like this one that shows up outside the integral. And this is evaluated at a point. So in a sense, it can be considered as some rule for the amplitude. So in this sense, this can be considered as some rule. What is the value of the amplitude at threshold? What is the scattering length? So by traditional subtraction, we typically recover an scattering length. Also, this dispersion relation now has a very correlated relation with the scattering length. That is kind of the answer. If you move the subtraction point to a different point in the energy region, then you will correlate your dispersion relation a lot to that given point. For example, I put it at this threshold, but I could have put it at 0. That is also related to other things. The subthreshold expansion, for example, that is called, and that can be related to KPT, so to chiral perturbation theory. So it's a way, for example, for us to weight differently the dispersion relation on different regions. So if you're interested about some expansion and you want to look at some observables, you might want to include subtractions there. If you want to look in another region, or for simplicity in this case, you want to put the numbers somewhere else. But at the end of the day, this is all contained within the amplitude. So it's like different observables that we can gather out of the amplitude, but it's not a different amplitude, it's just the same one.
So you can kind of just, if you have the entire amplitude and then you start writing down your dispersion relations to relate the real and imaginary parts, if you piece them together and you don't get the original amplitude, would that tell you that there needs to be a subtraction term somewhere?
It's not exactly the subtraction term,
Okay.
but what that is telling you is exactly what we were discussing before. This is a very good question. What it's telling you is that these two are not compatible, right? This is exactly what you said.
Okay.
If I get the fit to the data, I have my real imaginary parts, then I compare to the real imaginary parts that I get from the integral equation, right? And then they do not match. Is this what we are asking?
Yeah, yeah. Exactly.
So this means that we are violating cross-check. Because if we were respecting cross-check, then the two of them will be equal. If they are not, it means that we are not applying the 3 first principles. And so this is what we have to do. We have to make them to be compatible. And you do that by just varying the parameters of the original fit to the data a little bit, so that you recover something that is compatible. So now this real imaginary parts match.
Thank you.
More questions for Arkaitz?
Yeah, it seems like everybody wants some rest.
I have one actually.
Yeah.
How can you guarantee that when you build your dispersion relationship, they are model independent and you can just look any model and you are sure that that's going to be your final answer?
Yes. So this is within some bounds.
Okay.
So within some bounds. So if the data is horribly grown, then there is nothing we can do. Okay. And let's say the data is just slightly grown. So then you can see that within those soft bounds, whatever model you use to describe the data, they will all be slightly different because they have different parameters, different expansions, so they will fit the same data. But they will have some epsilon of difference here and there. If they all fit the data, they cannot be very different, right? But they will be initially, there will be some differences. The idea is that whatever one of those you use, if you impose the dispersion relations, the result at the end of the day is 1 and is unique. So if you start within those bounds, and then you constrain up to full solution where everything is identical, then this is a pole, and with some errors when you propagate your errors. But that means that within some bounds, within some spread, you can have like 10 different models describing the same data, and then when you constrain dispersion relations, then 10 of them will converge to the same point. And this is what we call model independent. Okay. Any more questions? I think we are done with these lectures. Hope you guys enjoyed it. I'm gonna drop some bibliography today on the Slack channel and some papers that you might find interesting. And I'm gonna be around here at JLab. So if you don't find me in this room and you want to talk to me, I'm in the theory center most of the days. And you can also drop me a message on Slack and we can chat. Thank you.